Project 2.5, I2C Data Logger. This project explores wired communication protocols using two rails common between multiple peripherals and controllers. There's a shorter video explaining the process of this project. You can see the video link in the description. I2C, or I2C, is short for Inter-Integrated Circuits. As mentioned, this project uses the rails SDA and SEL, short for serial data and serial clock respectively, in addition to power and ground rails. This system of rails is known as the I2C bus. This bus requires a master piece, which is usually a microcontroller, and multiple or just a single peripheral. To ensure a default definition of high and low signals, both the SDA and SEL rails are pulled high with resistors to their rails from the power line. Each peripheral has its own 7-bit address, which is used by the microcontroller master to identify and communicate with each part individually. There are a couple of phases to an I2C communication process. The first is addressing, starting with the start condition. During this phase, the master pulls the data line low and all the peripherals come out of a free or dormant state and pay attention to see if the address that the master sends out is theirs. This phase also starts the clock pulse, which is used throughout the rest of the communication cycle. A peripheral with an address matching the one sent out by the master during the start condition acknowledges the reception of the address by pulling the data line low. Then, communication between the peripheral and the controller continues while the rest of the peripherals go back into their resting or dormant phase. Communication continues with the clock pulse running, and then 8 bytes transferred along the data line with an acknowledgement on the other end of the transmission reception. After the transmission cycle is complete, the master stops running the clock pulse and the transmission between the peripheral and controller ends. This is the circuit diagram for the I2C data logger. The components highlighted in green are connected to the SCL rail, and the components highlighted in orange are connected to the SDA rail. There are 7 construction phases to this project. The microcontroller, the HID controls human interface device, the DS1307 RTC, the TC74 temperature sensor, the EEPROM components, the OLED display, and the exterior design elements. For starters, the exterior design intended to have a permaproto board 6 inches long attached to a 3D printed case. However, the permaproto board was really bad quality, and the components used to connect the appliances to the permaproto board were also really bad quality, and the system did not end up working. It does work on the breadboard, so we'll use these components as the example. On the Arduino Nano, the serial data and serial clock lines are designated as pins A4 and A5 respectively. 2 of the long breadboard rails were designated for SDA and SCL rails. The next piece added is the real-time clock, which contains the data for the active hours, minutes, seconds, day, date, month, and year. As long as it's connected to power, it's able to consistently update the data within its storage accordingly. The data is received from the computer from a special example code in the time library. It's also able to provide a constant square wave output, which is used for an interrupt function within the program. The next added piece is the I2C compatible TC74 temperature sensor. This piece is pretty self-explanatory. Following that, the 24LC256 EEPROMs are the next pieces added to the circuit. These components store data that is recorded from the TC74 temperature sensor and the timestamp alongside it, and is drawn upon when asked for history by the HID controls added in a later phase. Up to 8 EEPROMs can be used on a single circuit, as the address used for the I2C bus can be modified. The modifications occur within the pins A0, A1, and A2, dependent on whether they're wired to power or ground. Then the OLED graphic LED display is added. This display is 128 pixels wide and 64 pixels high. The OLED display and the data that is presented on them from the EEPROMs is controlled by the status of the HID human interface device controls attached to the ATmega328P microcontroller. There are several elements of the software to mention. The first is that the first condition, the beta condition, occurs when the system is initiated and the top of the hour has not yet been met. During this phase, the data is read from the TC74 and put straight onto the OLED display with the timestamp and not stored to EEPROM. HID controls cannot be used to alter the display. Once the program has run through the top of an hour, the main phase begins. During the main phase, each second, the data from the TC74 temperature sensor is recorded and averaged out to compile for a minute, and then again to compile for minutes to hours. Then the HID controls are enacted upon. There's a switch and a potentiometer. The switch is meant to determine which type of display is shown on the OLED. The potentiometer position determines how much history is shown on the OLED display. The data can either be presented with an active timestamp and the temperature of however many hours ago, or in a dot plot formation where the variables are constrained to -24 and +40 Celsius. Thank you for listening.